Hello everyone, myself N. Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the last session, we discussed about shear flow and torsion in the wing and fuselage, and now we are going to extend our analysis to stress analysis of wing sections. Now in the present module, the learning outcomes at the end of this module, the students are able to analyze wings that are subjected to bending, shear and torsional loads, and then we are going to solve problems on wings with booms. So this is a particular case of a wing section in which the wing is subjected to 3 boom shell. So in the previous problem, we have seen different cross sections, different parts of the wing in which there are many booms, more than 3, 4, 5, the number of booms are present. But this is a special case in which only 3 booms are present, and you can see in this diagram that there is boom 1 and there is boom 2 and there is boom 3. So if such a case is there when the wing is having only 3 booms, then the analysis will become much easier and no need to go for the analysis of which we presented in the previous sessions. But rather than what we can do here, it is the analysis easily, that shear flow can easily be calculated by applying the equations of equilibrium alone. So we know that the 3 equations of equilibrium, that is the force equilibrium in along x direction and the force equilibrium along y direction and moment about any particular point that will be equals to 0. So by considering 3 equations of equilibrium, we could able to calculate the shear flow in this 3 boom shell. So therefore, we'll consider this diagram now and let's see how we can able to do that. So let's consider a wing which is shown in figure and which is having 3 booms, 1, 2, 3, and let us try to represent the shear loads here. So Sx is the horizontal shear load and which is represented at a distance of neta naught from the line of action of boom 3, that is a horizontal line of action of boom 3, and then we have got Sy, which is a vertical load and which is a distance of zeta naught and which is acting from the line of action of web 1-3. So this is zeta naught. So Sx and Sy are the horizontal and shear loads, and also let's try to represent the shear flows. So from 1 to 2, let the shear flow is Q12, and from 2 to 3, let the shear flow will be Q23, and from 3 to 1, let the shear flow will be Q31. And also let's try to divide since we need to take moment, and here in this particular example we are going to take moment about 0.2. So that what we are trying to do here, it is dividing the areas from 3 to 2 and writing these 3 areas as A12 and A23. So this is A12 and this is A23 area. Okay. So and the lengths also you can see here, and from this boom 2 to 3, the length is L12, which is same as L23. Okay. And the height from boom 1 to boom 2, the height is H12, whereas from boom 2 to boom 3, that is the height is nothing but H23. So total together you can consider this height as H. Okay. So in this way we considered all the distances, shear flows and the loads that are acting on this 3 boom wing shell. So let's try to solve this. So resolving the horizontally and vertically, noting that the resultant of the internal shear flows is equivalent to the applied load. So now what we are doing here, we are taking this condition that the resultant horizontal load must equal to the horizontal equilibrium that is due to the shear flows, and similarly the resultant vertical load Sy, that should be equal to again the equilibrium due to the vertical shear, that is the shear flows. Okay. So let's try to write that. First, if you try to consider horizontal equilibrium, that is summation of all the forces in x direction, if you try to write, and the horizontal shear load, what we have here is applied shear load is Sx, and that should be equal to the load, that is the force equilibrium due to the shear loads. Now let's try to see the shear loads, and here in the horizontal direction, now Q12, this is just like the, you can see that this is just like one inclined force. Okay. So like Q12 you have like this. Okay. Again it will have 2 components. One is a horizontal component and one is a vertical component. and we are not concentrating on angles much because this is very, very small. And so therefore what we need to try to write here it is, instead of taking this as incline, so we are, since this is very, very small angle and we are considering is almost equivalent to the horizontal, so q12, now in this direction we are taking q12, and which is taking in the negative x direction here. So q12, you can approximate it in the negative x direction. I am writing minus q12 into its length on which it is acting is nothing but L12. So q12 into L12, that is the force equilibrium due to 1-2. And if you look at it even similarly 2-3 also, 2-3, the shear flow is like this, and you can consider in the horizontal direction, that is 2-3, and you can consider q23 and its length is L23. Okay, so this is how we consider the equation of equilibrium in the horizontal direction. Similarly, if you try to write sigma Fy, that is forces in vertical direction, so the applied shear load is Sy, and that should be equal to, now again similarly here, if you try to look, this is a straight force q31 which is acting in the upward direction, so you can take positive, so q31 into its length is the combination of both, that is the depth h12 as well as h23. So I am writing h12 plus h23. Okay, and similarly, and when we consider the force as q12, as we discussed that it is a slightly inclined force, it will have horizontal component. Though we are not using angles here, we are writing the components. So the vertical component of that q12, it acts in the downward direction, so therefore it should be considered. So I am writing here minus q12 into q12, and from here to here 1-2, the depth is nothing but h12, so that you have to write. So q12 into h12. Similarly, this q23 also, if you try to write, so this inclined is this one, horizontal, if you try to draw this one, so inclined is q23, and it will have a horizontal component that we have used in the horizontal equilibrium, and the vertical component acts downwards. So similarly for this also you can write minus q23 into, and its depth is nothing but h23. So h23, that you have to consider. Okay, so these are the two equations of equilibrium we got. Okay, similarly now we are going to take the moment, and now in this we are going to consider the moment about boom 3. So therefore what you can consider here is, so we are taking moment about boom 3. So again the moment equilibrium is also you have to write in a similar manner, like the moment due to the shear loads, that must be in equilibrium with the moment due to the shear flow. So in the left side of the equation we write moment due to the shear loads, and in the right side we try to write due to the shear flows. So left side, if you try to write moment, when you are taking moment about this one, so Sx is the horizontal shear load and its perpendicular distance is neta naught. So therefore we write Sx into neta naught, and then it gives the clockwise moment about boom 3. And similarly Sy is the vertical shear load, and zeta naught is the perpendicular distance about the line of action of the point 3 or boom 3. So again it gives the clockwise moment Sy. So Sy into zeta naught is the moment. So this is the moment due to the shear loads on the left hand side. Similarly on the right hand side you have to write moment due to the shear flows. And when you look at this one, and at 3 you have got two areas, A12 as well as A23. So it is easy for us to write in terms of torsional moment. Okay, moment you can write using torsion equation, that is T equals to 2AQ. Okay, torsional moment. Okay, and so that you can write 2 into area of the cell into respective shear flow. Okay, and when you try to write this moment, and both q12 as well as q23, it's going to give anti-clockwise moment about about boom 3. So therefore we'll write minus, and 2 into A12 into Q12, A12 into Q12, minus 2 A23 into Q23. Okay, and then after writing this one, what you can do here it is, you can consider this Sx horizontal equilibrium equation as first equation, and this was second equation, and the moment equation you can consider it as third equation, and you can solve for these three simultaneous equations, and then you are going to get the shear flows Q12, Q23 and Q31. Okay, so that is the three boom shell wing analysis. Okay, so rather than going to find out shear flows using different methods, so it is better to use this equations of equilibrium so that easily we can predict the shear flows in the three boom wing shell. Okay, so now let's try to move on to the next one. And now what we are considering here, it is wings which are subjected to bending. Okay, so wing when it is subjected to bending, that is bending moments, and we try to see the effect of it, and then we'll try to calculate the direct stress in the booms. Okay, so let's look into this one. So bending moments at any section of a wing are usually produced by shear loads at other sections of the wing. And when you consider a question, the wing section shown in figure has been idealized such that the booms carry all the direct stresses. If the wing section is subjected to a bending moment of 300 kilonewton meter applied in a vertical plane, calculate the direct stresses in the booms. And he has given the boom areas. B1 equals to B6 equals to 2580, B2 equals to B5 equals to 3880, and B3 equals to B4 equals to 3230 mm square. Okay, so this is the problem of wing section which is subjected to bending moment, and he has given a bending moment of 300 kilonewton meter, and he mentioned that it is applied in a vertical plane of symmetry. So vertical plane, so when it is applied in a vertical plane, it doesn't mean that it is nothing but bending moment mx. And you can write this 300 and you can reduce, you can convert this 1 kilo into 10 to the power of 3, and then for meter also if you try to convert, you are going to get another 10 power 3, so you are going to get 300 into 10 to the power of 6 Newton mm. Okay, so this is a bending moment. And also, and if you try to look at the symmetry, okay, now is this figure is symmetrical about a horizontal axis? That means if you try to draw one horizontal axis like this, and you can see there is a hollow portion here. Okay, this is a hollow portion, and then and above you have one panel like this. Okay, but by looking at the geometry of the diagram, you cannot say that it is symmetrical about horizontal axis, even though the left side, that is cell 1 and cell 3 are symmetrical. But when it comes to the cell 2 in the middle cell, it is not looking like a symmetrical diagram because of the portion that is there here. Okay, but still this kind of diagrams, wing sections, you can consider as horizontal axis of symmetry even for the second cell. Okay, so how can we do that? Because the more important thing here in this question is nothing but the boom areas, how the boom areas are distributed. So if you look at the boom areas, B1 is equals to B6, B2 is equals to B5, B3 is equals to B4. So these boom areas are equally divided on the upper and lower surfaces of the given wing section. So therefore, it is reasonable to assume that this given wing section is symmetrical about horizontal axis of axis. So based on the distribution of the boom areas. So therefore, you can consider for this diagram Ixy equal to 0, that is the product of inertia, and horizontal shear load is not given, so that our formula for direct stress distribution reduces to mx by Ixx into y. You can consider this as first equation. Now for this question, you need to calculate the moment of inertia. Now how moment of inertia can be calculated? Moment of inertia is nothing but summation of b into y bar square, okay, or br yr square. And now like that we got 1, 2, 3, 4, 5, 6 booms are there. So what you can do is you can calculate moment of inertia for the upper half of the section, and you can multiply by 2 so that you will get completely for all the 6 booms. So first starting with the boom area of 1, that is 2580 into the distance y bar square, that is from here to here the distance is 165. So we'll write 165 square plus, next coming to boom 2 area, that is 3880 into the distance from here to here is nothing but 230. So we'll write 230 square plus the third boom is nothing but 3230 is the area, and its y distance from here to here centroid is nothing but 200 mm. So we'll write 200 square. Okay, and then you try to do this calculation, you are going to get Ixx. So once you get this Ixx, substitute in equation 1, and then mx also you can substitute. So you will get sigma z equals to some constant into y. Okay, so that will be the equation number 2. So the moment of inertia we got here, that is 809 into 10 to the power of 6 mm power 4, and after substituting sigma z equals to mx, that is equals to 300 into 10 power 6, and then Ixx equals to 809 into 10 to the power of 6 into y, and that will be equals to 0.371 into y. Okay, so this is the stress distribution, and you can consider this as equation number 2. So sigma z equals to, we got 0.371 into y. So this we got, and after that what you can do here it is, and you can go and substitute for respective booms. So we got sigma z, that is equals to 0.371 y. So we got 6 booms in this diagram, so that you can substitute easily. For example, if you want to try to find out sigma z, that is the direct stress in boom 1. So we'll try to substitute 0.371 into the y distance of boom 1. So from the diagram clearly the y distance of boom 1 is nothing but 165. So we'll try to substitute 165 mm. Okay, and that you're going to get, it is a 61.2 Newton per mm square, and it is similar to boom 6, but it is of minus 165 is the y distance. So therefore you can write this is equivalent to sigma z 6. Okay, that you can see here. See, 61.2 and boom 6 60 minus 61.2 Newton per mm square. Similarly, sigma z2, that is equals to 0.371, and the boom y distance from boom 2 is nothing but 230, and we'll substitute here 230, and you're going to get this one, the boom stress, that is equals to 85.3 Newton per mm square. 85.3 Newton per mm square. Again, this is equivalent to sigma z, what is that, 5. Similarly, the third stress, that is the stress in boom 3. So you can write sigma z3, that is equals to 0.371 into the distance is 200, and you're going to get this as 74.2 Newton per mm square, and which is equivalent to again sigma z4. So in this way you can calculate all the boom areas and respective stress, direct stress in all the 6 booms. Okay, so this is how we calculate the boom areas and the respective stresses in all the booms. Now if you try to look at into the next topic, that is torsion. So when you have a wing section which is subjected to torsion, and if it is having more number of cells, more than one cell, and you can, what you can consider is, you can consider this example in which we have 3 cells, cell 1, cell 2 and cell 3. Okay, and the torque is applied, and then you can assume the shear flows in each cell separately, and the diagram may have n number of cells. So it may have n number of cells, and it carries torque T, which generates individual but unknown torques in each of the n cells. So each cell therefore develops a constant shear flow Q1, Q2, Q3 and so on up to Qn. Then the torque equation is given by T equals to summation R equals to 1 to n to AR QR. Okay, so that is for example, if the cells, you have one cell, so you can write T equals to 2A1 Q1, and if you have 2 cells, you can add 2A2 Q2, and if the 3 cells you are having, you can add 2A3 Q3 and so on. So this is the torque equation. So whenever the wing or fuselage, when it is subjected to torsion, the first equation you can use is torque equation, and the second equation what you use is rate of twist. So rate of twist, the d theta by dz, that is equals to 1 by 2 ARG cyclic integral of Q ds by T. So now what you do is, first you will write this torque equation, then you write rate of twist d theta by dz for cell 1, and you write that equation. then you write rate of twist in the second cell, that is you'll write another equation, let this be equation 2, let this be equation 3, and then you'll write rate of twist in third cell, and that is, let us consider fourth equation. So now you got fourth equation, and you'll assume the shear flows in this is Q1, and this you'll assume it as Q2, in this you'll assume the shear flow as Q3. So our aim is to calculate the shear flows Q1, Q2, Q3. So you got four equations here. So this of torque equation is first equation, and here you got 2, 3, 4, that is rate of twist in each cell separately. Now the compatibility condition here, what we use is nothing but we write twist in first cell is equal to twist in second cell, because the same torque is applied on all the three cells, therefore they twist by the same amount. So by taking this compatibility condition, since the same torque is applied on all the three cells simultaneously, so each cell twists by the same amount. By taking this as the compatibility condition, and we'll equate twist in first cell to twist in second cell, and then we'll write this as equation number 5. Similarly, the twist in second cell will try to equate to the twist in third cell, and we'll write this as equation number 6. Similarly, twist in third cell also you can equate to, if it is required, you can equate to twist in first cell, and you can write this as 7th equation. Okay, so finally we got 5, 6, 7. So now the equation numbers 1 in along with 5, 6, 7 equations, if you try to solve simultaneously, you are able to get the shear flows Q1, Q2, Q3. Okay, so this is how the procedure of torsion that will go here like this. Okay, so therefore any wing or fuselage cell, when it is having either one cell or two cell or three cells, so this is what the procedure we have to calculate. And first we have to write the torque equation, then we have to write rate of twist in each cell, and then we have to take the compatibility conditions, and then we can use this equation numbers 1, 5, 6 and 7 to solve simultaneously, so that you can able to predict the shear flows Q1, Q2, Q3. Okay, and then for example, you may use the rth cell. For example, when you try to use N cell wing section, sometimes G may be constant and sometimes G may not be constant. So if G is not constant, if G is varying for all the walls, so what you can consider here it is, you can slightly modify the rate of twist formula. What I am doing here it is 1 by 2 AR, I am adding G reference, and then here for G I am dividing by G reference. So I am adding reference G reference as multiplying and dividing in this equation, so that the G by G reference I am taking that this ratio, and then G reference value is nothing but is a convenient reference value of the modulus of rigidity, and therefore it can be equated to T star. The G by G reference, the ratio is called as T star, and T star is called as modulus weighted thickness. It is simply given by T star is equals to G by G reference into T into thickness. So completely this G by G reference into T can be removed and replaced by T star, so that what you can write in this equation is nothing but cyclic integral of ds by T star you will write in this equation, and therefore and this you can write it as delta. Okay, so this is how we'll take, and for all the values for all the walls he'll give different values of G. You can choose any one modulus of rigidity as a G reference value and start finding its T star. So you will find out a T star for 1, 2 walls, 2, 3 walls and so on, and therefore you can substitute in this, but the procedure will be same like just we discussed in the previous analysis. Okay, so that's all from today's session. In the next session we'll try to solve problems corresponding to wing and fuselage. So thank you everyone for watching.